Energy in simple harmonic motion. I think I had said that it was going to be the next lesson, but we ended up doing the experimental lesson. And so now here it is, energy in simple harmonic motion. So the in simple harmonic motion, we have a transfer of energy back and forth, of course, between kinetic and elastic potential energy, right? It would go on forever, and if there wasn't friction, that's kind of the very last slide. We're talking about reminding you of the idea of damped harmonic motion when there is friction. And so, yeah, it would just keep going back and forth like a sine curve, where the total energy would always be the energy stored in the spring and the energy of motion, kinetic energy of the thing that's bouncing back and forth, right? So the total energy would stay constant if there wasn't friction. Whether you have a spring bouncing back and forth like that, or you picture the different situations here. You've got when the mass is way over here, that would be all of the elastic potential energy. When the block is way out here, that would be again all elastic potential energy. This would have been compressed in the system, and this would have been stretched in the system. So either way, it's still storing energy. When you let go, the mass moves one way or the other, just opposite directions. And then in the middle, all of the energy would be kinetic. Right? The spring is naturally sitting in that position, so it doesn't have any force. So all of the energy would have been converted into kinetic. Right? So that's the idea that we want to be aware of course. So maximum energy I was just talking about in the middle, where there's no so maximum elastic potential energy would be at the edges, right? When you have full stretch, so the full amplitude of stretch, compression in or stretch out. So this little app will probably work for 5 minutes for us this time. There we go. So this guy here, expand this thing. There we go. You press play. You can see the pendulum go back and forth, and it's kind of nice. You can see the energy transferring back and forth between potential energy and kinetic energy. The total is always the same. Okay, so at any point, if I pause this, try and get it close to the center here, most of the energy is kinetic, right? And then press play again and pause, and you get out to the end, around there somewhere, most of the energy being potential energy or elastic potential energy. If it was a spring, in this case, gravitational potential, if it's a pendulum. Yeah. So, and then there's that curve of potential energies, curve of kinetic energies, so elastic potential and kinetic, and then see how they alternate between one another, and then total energy should expect to be the same amount the whole time, the addition of those two curves. All right, so that is an animation of the ideas we're talking about for you. So conservation of energy, as you can tell, is a kind of a big part of this, right? Because the energy is staying the same for this frictionless version that we're talking about first. And so if we're starting with 10 joules of energy, it's going to stay as 10 joules of energy as you go through your work, right? So you've got the initial energy, and then it's going to really is actually going to be an elastic and a kinetic, maybe on both sides, but typically you stretch the spring to its starting position, or you move the pendulum to its maximum position. So we're thinking of that as the starting energy, and then at any given time you have that energy divided up between these two types. Okay. So yeah, if there wasn't any frictions, would stay the same as we said before. And I mentioned also the initial energy, like you could think of an initial state where you had a certain amount of elastic and a certain amount of kinetic. That would be fine as an initial state as well. So possible combinations, of course, you could have all of your energy as elastic, in which case you'd be all of the 10 joules there. So that pendulum would have no velocity, right? So it would be all the way compressed or all the way stretched. So all the energy stored in the spring and at max amplitude, either left or right, or up or down, or wherever you're talking about, right? Whatever the situation may be. Or you could have all the energy as kinetic. And so that would be a scenario where it has no elastic potential energy, all of it's kinetic. So that'd be at the center location where it's moving the fastest. And the spring's just in its natural position, so no energy. And you could have some combination between, right? Somewhere in between. So where is this one? Where's this one here? It is got more energy stored as elastic, right? And so it's closer to one of the edges, right? Closer to one of the maximum amplitudes. All right, so calculations with this. If we have a spring mass system undergoing simple harmonic motion, the minimum length of the spring is 8 and the maximum length is 25. Determine some things. Determine the length of the spring at its rest position. Determine the amplitude of the simple harmonic motion. This question, you've really have seen something like this in your 3U grade 11 functions course when you're talking about the sinusoidal, right, sine curve. So it shouldn't be too big of a surprise that that's coming up, given that that's the shape of the motion we're talking about here, right? But if you want to just visualize this in the physical situation here, got the minimum length is 8 and the maximum length is 25, right? And so you're visualizing this thing, and they're going to ask you the rest position. And so really that rest position, you can tell, is like the middle of those two, right? And so that is just add them up and divide by 2, right? So that's the same as, really the same as getting your, I don't know what to call that. Anyways, sorry, that's your vertical shift, right? It was called. And then your amplitude is the maximum distance, or the difference between them, sorry, divided by 2. Okay? So yeah, that would be the answers to those. Just plug numbers in, get that. Other types here is a little more, what the majority of the kind of questions would be, right? But so you have a 55-gram box attached to a horizontal spring. Quite often it's a horizontal spring, so you don't have to worry about gravity in a situation like that. The spring is then compressed to a position 8.6 centimeters to the left, and then released. So this is, like I said, the initial position here. All of it is elastic potential. So you just think of that as the starting amount of energy rather than a bunch of energy types at the start. So it says questions here. What is the speed of the box when it's at 5.1 centimeters from equilibrium? And what is the maximum speed of the box? Okay, so to go through this, that's just your given information. We want to know the speed. We know that's where we're at. And so really you've got this idea that the total energy at the start is equal to total energy at the end. And so you've got your elastic and kinetic equals your elastic and kinetic at any point in time. The starting one in this case is all just elastic, right? So we're going to see the calculation is just going to be all elastic potential energy. You have your 1/2 kx squared. They have A for the amplitude, because in this case, the x is the amplitude, right? That was the initial full compression. The kinetic energy at that point, 0. And then the elastic potential energy stored when you're at the compression distance of 0.051 meters. It's going to be that x value in there. And then you're going to have your mass, and you're going to be able to find determine the velocity, right? So I think things simplify to that by just multiplying by 2 everywhere. And here we go. So there's the where we were at. And so numbers go in. You've got your 24, and you've got your amplitude in there, and you've got your current location, current amount of compression. K values are in there, all the mass is in there, and just solve for V, right? So step by step, solve for V, get 1.4, right? Note that this velocity could be to the left or the right because it doesn't specify which side. That is not really what this plus or minus is telling you, but convenient that it's kind of there. But I mean, that's not a mathematical meaning. It was more of an interpretation of the situation, why we would conclude this, that it could be either way. Sometimes the math results here tell you things, right? Physical meanings, but that's not really the case here. This is my preference, really, to be honest. I just plug numbers in and calculate, right? The online version had this on it originally, and so I like to show detail here, so I did that. Not my preference for this, but I mean, it does have its advantages for carrying decimals, right? You'll see along the way here, I'll have sometimes I'll have ... dots, meaning I'm carrying more decimals like that right there. And then I'm rooting that and getting this. And then eventually I'm rounding, of course, to a reasonable number or the correct number of significant digits. But yeah, I think the correct number of significant digits was just 2, right? That's why that was rounded to 1.4. If you did, just use the variables, solving for v would end up like this. And so you could plug in the numbers and get that, which would have its advantages for the rounding issue, right? Because you more likely have these numbers in the calculator and this squared and then take away that squared. And, it's all at once, right? All the calculations are all at the same time. Maximum speed of the box. So that's when we're going to have no compression at all. In other words, we're in the middle. So set that to be true, in which case basically you're going to have your elastic potential energy is equal to that kinetic energy. The kinetic energy is equal to the full energy value. And again, plug in numbers and calculate out. You get 1.8. So using, you can tell my preference here, using this hard to recognize, hard to memorize, hard to interpret version, you could do this as well and plug in the zero value and just calculate it all out. So we'd have the a squared, take away 0 squared, it's just the a squared, right? The amplitude squared. And of course spits out the correct number, but no one is going to list, no one's going to memorize that for sure. And if you had it as an equation, I still, it's such a specific case, right? So I don't think it's considered an equation that would make it onto many people's equation sheet. This kind of knowledge process here really drives the process and allows you to tackle a wide variety of situations rather than just using a particular equation for a particular case, right? So total mechanical energy in a system consisting of a block attached to a spring is 7 joules, 7.00 joules, so 3 significant digits. Motion is frictionless and horizontal. Again, no complications due to gravity. The force constant is 120.0, so 4 significant digits there, but we're going to be limited to 3 in the end. And it just asks things like what's the maximum amplitude and what's the maximum speed it gets and all the usual stuff, right? So for the first part here, we had maximum amplitude. So we're going to want, for maximum amplitude, we're going to have the kinetic energy be 0, right? So you're going to see in your initial energy equals your final energy situation, the kinetic energy is going to be 0, right? That's why there's nothing here for that. And then plug in values and solve and so on. However, they solve for x and then plugged in values, but it's going to give you the maximum amplitude. Well, that driving concept there was for maximum amplitude, we're going to have full compression, we're going to have no velocity, right? So kind of an important thing to recognize as a starting point as part of your process. Okay, so same kind of thing for this next one. We've got, what would the maximum speed be? Well, that's where you're going to make all of the energy be kinetic, right? So I have an initial and a final idea again, right? Where we want maximum speed. So the elastic potential energy is going to be 0, right? And so in this case, that one's gone. And so you're left with just the EK, 1/2 mv squared, the kinetic energy, right? And again, solve for V or plug numbers in and then solve, or solve for V and then plug numbers in, either way, right? They're rounding down to 2 significant digits there from the original online stuff from the ministry. Yeah, I guess so there, right? Because of that, 0.55. There you go. So got that. The next one was, what's the speed of mass when it's a certain distance from the equilibrium? Well, that is going to have the original, all of this stuff still, but we're going to have a value here based on the compression and so on, right? And so we go ahead and do the normal stuff, right? So you've got the original amount of energy equals a certain amount of elastic and a certain amount of kinetic, a certain amount of elastics based on the 10 centimeters. So there it is, 0.100 meters, because that was 3 significant digits. That's why I put it like that. And I was limited to 2 in the end anyway, so I could have just put it as 0.10 or whatever, or even just as 0.1, but the same thing, obviously. Yeah, so calculate a value, subtract that from both sides, and divide out that 0.275, and square root both sides, technically plus or minus answer there, but we're just looking for the speed, right? So we get 4.8. so there's that 2 significant digits that are minimum of what we started with. And finally, what would the period of this be? That's when you're like, okay, hopefully that's when you're like, okay, I remember learning about this. I'm going to go look up that formula and I'm going to plug numbers in, right? So the period of a spring mass system is this formula. And so you plug in pi and you plug in the mass and you plug in the spring constant value and you calculate it. So that's a bit of a blast from the past review kind of thing going on, right? That absolutely could throw someone for a loop at any point in time because it's just an equation that you probably don't have memorized, but you have to just find it in your notes, look it up on your equation sheet, whatever, right? That is the idea. So this little link here is just an animation of simple harmonic motion. And the nice thing is it shows all sorts of things. When you run this, you can see the kinetic energy and the elastic potential energy sort of swapping, switching places, if you will. At any given time, if you were to pause, say when it's out at the very edge, notice how you've got, if you look at the definitions here, the U is, I had this sorted out, but by red here, the spring's potential energy is at the maximum. That makes sense because we're at the very edge. The green is the kinetic energy, and so that's at 0 because we're at the edge and it stopped. It started, getting ready to go on its way back, all the way along here. Like the position of it bouncing back and forth, the speed of it bouncing back and forth, the acceleration bouncing back and forth. Like when is the acceleration the most? Well, right now, right when it's at this spot. So acceleration's at a maximum there, at a peak at the bottom, right? Pulling in the negative direction in the maximum, and so on. So it's all sorts of stuff there you can analyze. There's one question in the textbook I didn't include in the assignment, but it had a graph like this. So if you take a look at that question, this simulation, and you see the energies bouncing back and forth between the different forms. I think the simulation helps you interpret the picture that the textbook had in there. And of course, the idea of the damped harmonic motion. In reality, of course, there's going to be some friction. So the nice thing about, and I mentioned this in the past, right? It's nice to have this like conservation of energy version of things, because then there's a spot to put, natural spot to put the other form of energy, right? So picture this eventually becoming that whole 10 joules, in which case we started out with 10, we end up with 10 as friction and heat. So nothing left in either of those. The spring isn't compressed anymore and the thing's not moving. In other words, it's slowed to a stop, right? An animated or simulated version of this is here. I think I want to go to the energy one. I'm going to get rid of that because it's just all sorts of stuff. We need to look at it. But this spring bounces back and forth, and eventually all of that energy dissipates away into heat because it has a damping amount, right? And so if you're looking at these, the rate that this tapers off, and the rate that tapers off shown there as well, that depends on how much friction there is, how much damping there is, right? So the nice thing in this little program, wrong window here, in this program, you can change that amount, right? So if you make it be a lot, give it a whole bunch of energy, and it dissipates away really quickly. So that would be this curve dropping off extremely quickly. And then if you had it at a sort of a medium value, it drops off fairly quickly, but takes a little bit of time. It would be lovely. I couldn't find. It'd be lovely if I could find one that would graph the like this, right? Show the graph, but have it taper off. But I couldn't find one. So there you go. And that is all. So your practice assignment is there. And that's it. So here we go. All done. All right. Thanks for watching.